Hello everybody. Today we learn heap sort. What is heap sort? We'll review some equations from the master theorem. We'll talk about binary tree, fast talk, and we'll talk about heaps, heap property, heap sort, and heap data structure. Okay? The review, given a divide and conquer algorithm, an algorithm that divides a problem of size n into a sub-problems, each of size n over b, then the cost of each stage, i.e. the work to divide the problem plus combine solved subproblem, be described by the function of n, which is equal order of n power d. Then the master theorem gives us a cookbook for the algorithm running time. This, okay? We'll use this, okay, for time complexity to calculate the complexity of order of what. Okay, let's begin. Also, so far we have talked about two algorithms to sort an array of numbers. Merge sort. What is the advantage of merge sort? Who tells me? What is the advantage of merge sort?
سريع كثير.
سريع. شو الكومبلكسيتي؟
log n log n.
log n running time هو اسرع الجوريزم لهلا كسورتنج، اوكي؟ كسورتنج. بس عنده disadvantage. What is the advantage of insertion sort? The disadvantage of insertion sort هو بطيء n square. الاوردر تبعه n square الانسرشن سورت، بس عنده شغله حلوه advantage هي sorts in place. So we have something called sort in place algorithms, like insertion, like a quick sort, like heap sort, like today. Okay, we have different sorting using sorts in place. Shiani, what is the mean of sorts in place? Which will only need constant number for the auxiliary variables to sort the array or list by swapping. Okay. كل algorithm sorting بيستعمل swapping و for loop and swapping. هيدا بيخفف على الميموري لود بالكونستنت، وما في كتير كونستنت، only 2 or 3 constant بحلوا لك كل الالجوريزمز. سو هو بسموهم فيهم swapping sorts in the place. اوكي، insertion sort واحد منهم، والهيب sort اليوم هيكون واحد منهم. So next on this lecture we'll learn heap sort. So heap sort will combine the advantages of both previous algorithms. So heap sort will combine the two techniques in merge sort to get the complexity n log n. Heap sort the complexity also n log n, but using sorts in the place by swapping. So heap sort will use the both techniques in two different algorithms, merge sort and insertion sort. We'll see how. First, we'll introduce what is the binary tree. Binary tree contains parent node and children node. Okay. Your left, not screen left, your left called left children node and right children node. Okay. Binary tree, it's a binary. Binary, we have only two children, left and right. Only two case. So it's 3, 1 parent node and two children only, left and right. Okay, that's why called binary tree. Okay, now we'll go to heaps. What is the heap? We can see the heap can be seen as a complete binary tree, like this example. We have number 16, or root node. Here we have root node هون الأساسية هي اسمها root node. First left children, right children. Now this is a parent also, right, left. This is parent, right, left, right, no left, right, left. Here no children's here, no children's here. So this is called heap. Okay. What makes a binary tree complete? Is this example above is complete or no? حدا بيقول لي هذه التري محطوطه هي complete binary tree or missing something؟ منا complete لانه missing children's هون، صح؟ missing children's. So we call it nearly complete binary tree. We assume these children's are null pointer. Okay, we assume the missing children's, the incomplete children's, like as null pointer to name this heap binary tree as complete or nearly complete. Okay. Else we cannot solve any problem if it's not complete. We cannot solve anything. So we assume it's complete and then we assume the solution, like here. So heaps are usually implemented as array. Okay, and this array, A array, has index from 1 to 10 or from 0 to 9 or from 0 to 9. Okay, from 1 to 10. 16, 14, 10, 8, 7, 9, whatever. How to نوزعهم? Each node of the three corresponds to an element of the array that stores the value in the node. The tree is filled from left to the right. From left to the right. Focus on this, from left to the right. Okay. The first index will be the parent node, or root node, 16. The second will be the left, 14. The third, not children, the right children. So 1, 2, 3, 10. 4, 5, 6, 7, 8, 9, 10. Okay? So we'll fill it by rows, okay? Not by columns here, by rows. So 16 will be the first, 14 the left children, 10 will be the right children, then 8 will be the left children of 14, 7 will be the right children of 14, and so on. Okay? Any question here? Good. Continue. The property of heaps. To represent a complete binary tree as an array, we must follow these properties. The root node is always AI. The root node, the first node, must be AI. Node I is AI. Okay. The parent of node I is AI over 2. Integer division, like here. Here, I equal 4. The parent of 4 here will be I over 2, will be 2. It's true. Here we have children or node 5, I equal 5. The parent of 5 will be 5 over 2 as integer quotient part is always equal to 2. So it's true. So the parent of node I is AI over 2 as integer without decimal number, only quotient part. So it's true. Now, the left child of node I is always A to I, and the right to I plus 1. We'll see. 14. The left child will be 4 to I here equal to 2. Their children of 14 of node 2, their children will be 2i and 2i plus 1. Also, if we choose I equal to 4, number 8 here, I equal to 4, the left children will be 2i, 8. And the right children will be 2i plus 1, 9. It's true. Also here, also here, also here. Okay? So, if we have these properties, okay, so we can call it its complete binary tree. Okay? Else, it's not heap binary tree. Okay? Else, if you have any one is wrong, so it's not. We must be this and condition. All this will be true to get complete binary. To solve, again, later to solve it, how is, what is the complexity? Okay? Now, also, we have also a parent I, the value of parent I will be greater than or equal to the value of the children for all I. Okay? The question is, where is the largest element in a heap sorted? Who tells me?
أول element
The أول element الفوقاني صح. شو اسمه الأول element? The first element, what is called it?
البارنت وال
هو parent، كلهم parent، بس الأولين شو اسمه؟ شو اسمه؟ روت نود، روت البيز، الأساس. روت يعني الأساس البيز. روت نود الأساسية هي المفروض تكون the largest element in heap sorted. طبعا مش بنحيلها هيب، في يكون هيب منه سورت، نحن ما نعمل له سورت. وهلا حنشوف الالجوريثم. هلا حنبلش. هيب هايت قد ايه كبره او طوله للهيب. Definitions. The height of a node in the tree equals the number of edges on the longest downward path to a leaf. نزول بنقيس الهايت من تحت لفوق. الهايت عادة بنقيسها من الأرض للسقف، مش من السقف للأرض، من تحت لفوق. From bottom to top. So the number of edges from bottom to the node. Okay. The height of a tree, it is the height of its root. From the bottom till the first node, the root node. Okay? Example. Here. The same example. Here we have, okay, high equal to 0, the bottom. 8 and 7, height equal to 1, have 1 edges. 14, node 14, height equal to 2, 1 edges here, 1 edges here. The root here, we have 3, 1, 2, 3, from the left side. From the right side, here we have 3 and 9, height 0. 10, height 1. But we cannot say the root will be 2, because 3 is bigger than 2, so we'll take the maximum height between left and right. Okay? So the heap height, okay, it's the maximum number, the maximum height between left and right. Okay? You got it? Okay. To calculate, we have here complete binary tree here. Height equals 0, height equal to 1, 2, and 3. For level I equals 0, I equal to 1, I equal to 2, I equal to 3. So, number of nodes. How many nodes in the level 0? 2 power 0, 1. Correct. Here we have, in the level 1, we have 2 power 1, 2 nodes. Correct. On the level 2, here, 2 power 2, 4 nodes. Correct. And so on, and so on, and so on. Okay? Okay? So, what is the complexity? Oh, the height, sorry, the height. What is the height? If height equal k, any number here, k, so we sum this 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3 plus 2 power k. Okay, so 2 power I, summation from I equal to 0 to k, 2 power I. So we'll make the sum of all these must be equal to an element. So we have an element and we distribute this an element to binary tree. So this equation must be satisfied. 2 power 0 plus 2 power 1 plus 2 power 2, 2 power plus 2 power k equal to n, must be equal to n to be completed. So summation to I equal 2k plus 1 minus 1 equal to n. Then k equal log n plus 1 minus 1. Okay? Now k equal to h, so the h equal order complexity log n. Okay, plus 1 minus 1, don't care. So log n. Okay, here also, to get log n from this equation, we have some calculation. We don't care about this calculation, okay? Because k equal function of log n, it's log n. Directly, we can use it directly. Because we have plus, not times. If you have here division or times, different things. But we have minus plus, we don't care about it. Order of log n. Okay. Any question here? Any question? Good. Now, from the heap itself, how many sub-heaps the heap has? How can the heap has? Okay. As you can see, if these are elements, the last children, it's not a node because they don't have another children. So the number of heaps will be equal n minus 2, n over 2. Because here we have 2 power 3, 2 power 2, divided by 2. Each level, it's times 2. So back minus 1 levels to get these heaps. So each one of these are heap. Here, it's a heap. One parent node, 2 children. It's a heap. Here, it's a heap. It's a heap, it's a heap. Also, this node, it's a heap because have right, left, and so on. Here is the same, and the root node is a heap. So we have an n element, or n nodes, or an element. We have n over 2 sub-heaps, and n over 2 children. Okay, the last level, for height equals 0. Okay, for the last. Okay, so we will use this in the equation later. Okay, remember this. We'll use it in the algorithm. How to starting from n over 2. Okay, any question here? Okay, let's begin. How the Heapsort algorithm works. First, we will define a function heapify, which maintains the heap properties. Of course, the conditions to get a heap must be maintained. Given a node I in the heap with children left and right. Also given 2 subtrees rooted at left alone and right alone. Okay, assumed to be heaps. So left children with their children's will be heap. Right children with their nodes and children will be another heaps. As we said, sub-heaps. As we said before, it's a sub-heaps. Okay. Problem. If we have a subtree rooted at I may violate the heap properties. Violate is not ما بتساوي البروبرتيز اللي حكينا عنها. اوكي؟ شو بنعمل؟ We must let the value of the parent node satisfy the heap properties by comparing to its children. يعني إذا على left أو على right صادفنا إنه رقم المفروض الرقم الكبير يكون فوق ورقم الصغير يكون تحت. اذا صادفنا رقم البارنت هو رقم صغير والشيلدرن رقم كبير، المفروض نعمل له سوابينج. اوكي، هيدي لنحافظ على بروبرتيز تبع الهيب. الهيب على طول بيعمل سورتد رقم كبير للصغير from largest number to the lowest number. So if we divide the heap in the left subtree left or right, and we face a parent has a lower number than its children, so we swap it. This is the algorithm. This is the algorithm. So the algorithms or pseudocode of heapify array A for node I equal let L equal left I, R equal right I. If left less than or equal heap size of array, and AL which is the value of parent node bigger than its children, so the largest will be L, else will be I. Also, if R less than or equal heap size A and AR bigger than A largest, so again we swap it, largest equal R. If largest does not equal to I, so swap A مع I largest and repeat again. So this algorithm will sort in the top of the tree will be the largest number, and the children alone in the bottom of the tree will be the lower number. Okay, this algorithm. Okay, what is the complexity of this algorithm? It's a recurrence equation, recurrence function. Heapify, here we have if else, it's constant, no for loop, no while loop, but and the swapping, it's order of 1, it's constant, but heapify it's called itself recurrence, it's a recurrence equation or recurrence function. As before, how in chapter 4, how we solved recurrence functions or algorithms by 3 methods. Yes? Okay. What is the complexity of this algorithm? We did it before. It's equal to complexity of height. It's height. So it's order log n. So the complexity of this algorithm is order of log n. Okay? We'll continue. Example. If we have here unsorted heap, we will make it sorted heap or heap sorted. Okay? As you can see, we have error here. Violate the property. 16 is the biggest number in the list. True. 4, it's children 14. It's wrong here. It's not a heap, sorted heap. Okay? So we apply the algorithms heapify on node 4, on node I equal to 4 here, to compare it with its children. 4 in the left, we see that the node at the left is bigger, is larger than the parent, so we swap it. Okay? Again, 4, we see that on the left it's true, it's verifies the property 2 less than 4, but the right it's wrong, must be 8 at the parent and the 4 at the children. So again, we apply the heapify algorithm to swap these nodes. Okay, as you can see, from the children to the top. So we swap it. Now we check all the nodes. It's sorted heap. Okay, it's sorted heap here now. 16, 14, 10, 14, 8, 7 less than true, 8 2, 4, less than 8, true. 1, less than 7, true. 9, 3, less than 10, true. Okay, so it's sorted heap. Any question here? Any question how to its work, heapify? Good. Now, secondly, we have till 10 minutes. Secondly, we must define build heap. Now we sorted, but we must to build it. So we can build a heap in a bottom-up manner, okay, by running heapify on successive sub-arrays. من تحت لفوق، ما نعمل له sorting من تحت لفوق، نبلش من تحت. Fact, for array of length n, all elements in the range an over 2 to a1 are sub-heaps. اللي حكينا عنها قبل. We talk about this. So we have n over 2 sub-heaps. Okay? So walk backward, نمشي بالقلب, through the array from n over 2 to 1, calling heapify on each node. This is the algorithm. It's simple algorithm. Given an unsorted array A, make a heap. Build heap A equal heap size equal length of A. No, now for I equal length of A over 2, which means n over 2, okay, down to 1, heapify A مع I, الالجوريزم اللي قبل عمل calling للالجوريزم اللي قبل, okay, the previous algorithm. So this heapify will run n over 2 times, right? Right? N over 2 times, right? Not n times, n over 2. Okay? Do you have any question here? Good. Now, analyzing build heap. The heapify is sub-tree, takes order of h, time, where h is the high of the sub-tree. So, again, we previously calculate the order of h equal order of n, log n. But here we don't have n elements because we have sub-trees for each sub-trees, so we have log m number of nodes in sub-tree, okay? Also, the height of most sub-trees is small because we begin from the bottom to the up, so the height will be small. So, for n element, heap has at most n over 2 power h plus 1 nodes of height h. After complex calculation, very complex calculation, they prove that the complexity of built heaps is order n, not n log n, okay? It's n, okay? Because the height is very small for sub-tree, and because the height order of log m, so summation of logs will give us n, not log n, okay? So, finally, the Heapsort algorithm. Given build heap, an in-place sorting algorithm is easily constructed. Maximum element is at root node, A1. Discarding by swap the element of at an, decrement heap size -1, an now contains correct value. So, restore heap properties at A1 by calling heapify, also repeat the swap. Okay. The algorithms, the final algorithms will be like this. Heapsort, it's calling build heap. Okay, then for I equal length A down to 2, swap the root node to AI and let the size -1 and call again heapify. Okay, to make it sure it's sorted. To make it sorted. Okay, what is the complexity? Now we can say the complexity of build heap is order of n, and the complexity of heapify n log n. Thus, the total time taken by Heapsort will be order n plus n -1 order log n. By calculation, we make it so the Heapsort algorithms the complexity will be n log n and using swapping. So it takes the two advantage of merge sort and insertion sort. Merge sort, the complexity n log n, it's the biggest, and using swap. Okay? Okay. Any question here? Any question? Good. Now, where we can use the heap sort? Before, heap sort is a nice algorithm, but in practice, quick sort will be better. The next lecture will talk about quick sort, okay? Also in place sort using swapping, but it's better. But the heap sort will be used in the heap data structure. It's very useful there for implementing priority queues. Also, we have queuing in data structure. So this heap data structure, this heap sort will be used in the queuing system. Okay, it's another course called the queuing and modeling course. So also heap sort will be used in the queuing system, where a data structure for maintaining a set S of elements, each with an associate value or key. Example, the operation of insert maximum or extract maximum. Okay. Insert inside a set as an element X. Using heap sort, we can insert X in the sorted way in the set S. So using heap sort, we can insert X in the set S. Or return the maximum, it's the root node. Using heap sort in the S set, we can get the root node, which is the maximum number, right? Right, so we can use it in maximum S. And also extract max S, removes and returns the element of S, which is the maximum key, the same, okay? So these three functions in data structures, especially in the queuing of data structures, and it's another course, data structure. Sorry, did you take it? Did you take it, data structures courses?
ما هو prerequisite.
أخذتوه يعني؟ كثير.
لا أخذت بس.
كثير منيح. اوكي، مشان هيك استعملهم. اوكي؟ End of lecture. Any questions?
لسه باللاب نحن طالما كل اسبوع عم ناخذ اللكتشر الجوريثم معين باللاب بنطبقه ولا كيف
لا حنبلش نطبق الجوريزمات، صح، حنبلش نطبق الجوريزمات بالسي سي بلس بلس جافا او بايثون later. هلا اليوم today we have lab, we'll talk about this. Okay, we'll talk about this. Okay, any question? I will stop the record now.